is the Okanagan. And the Okanagan is just north of Tri-Cities of Washington. And I'm so pleased to be here where we can unite the voices of science, community, academia, media, government to discuss drinking water and water quality and issues. So I'm Terence Galbania, Peachland Community Drinking Watershed, and I'm one of the co-founders of the Peachland Watershed Protection Alliance. And very excited to be here again. Like I said, we are a 100% grassroots, nonprofit, nonpartisan, science-based, community-driven organization that advocates and informs on community drinking water issues, wildlife, wildland, wild places. So I am very excited to stay on and listen more to what Dr. Alila has to share with the larger community. Thank you.
Emily or Philip?
I guess I'll jump in here. Hello, I'm Philip Johnson. I'm the Conservation Director with the Oregon Shores Conservation Coalition. We're honored to be collaborating with NCCWP on tonight's video and on a lot of other things. Oregon Shores has been defending the Oregon coastal region's environment for more than 50 years now. We work on a full range of things from land use to water quality, to shoreline management, marine conservation, endangered species. We're perhaps best known for our Coast Watch volunteer program that keeps watch over the entire Oregon shoreline. As a regional group, we collaborate with a lot of different groups. So we're pleased to work with NCCWP on North Coast water quality issues. We work, for instance, with Friends of Otter Rock on the Central Coast on marine education and protecting rocky habitats. We work with Rogue Climate on the South Coast on estuaries and climate resilience issues. We work with Audubon chapters on such matters as offshore wind, drones in state parks. So as I say, collaboration is key because we do work regionally and need partners everywhere we work. We invite you to learn more about our work. Go to the OregonShores.org website to do so. Tonight's issue or tonight's presentation specifically focuses on more, shall we say, upper watershed issues, forest practices, and how they affect water quality, which is one of the many things we work on, but at the core, of course, of what NCCWP works on. One of the key things we are working on now has to do with estuaries at the other end of watersheds. Oregon is in the process of updating its estuary management plans for all of its major estuaries, and we're going to be happy to work with NCCWP on that end of watersheds, on water quality in the state's estuaries. So with that, I will hand it back to our colleagues there.
Hi there. Thanks for having us. My name's Emily, and I'm with the Lower Nehalem Community Trust. We are a land trust in the Nehalem region. So I'm calling in from the Oregon coast. We're on the traditional lands of the Clatsop, Nehalem, and Tillamook people. I want to recognize the original stewards and ongoing stewards of these lands. And as a land trust, we have properties from the headwaters down to the bay, and our mission is to protect land and nurture conservation values in partnership with an engaged community in our region. And our service region, which is the Lower Nehalem watershed, overlaps with North Coast Communities for Watershed Protection. And we are proud to be a collaborator with them on this and also other issues. And we're just very happy to be part of this webinar and to hear and learn from Dr. Alila. So thank you.
Okay, that represents all of our partner organizations, so I think we're ready to kick it off proper.
Can I share the screen?
Yeah, go for it.
Can you see my first slide with the title?
Yes. We can see it.
Thank you. Thank you, everyone, and thank you, Jacqueline, for the introduction. I want to thank you all for inviting me to be with you this evening on this presentation titled Forest and Water, New Science for a Changing Climate. This is my presentation outline. I'll introduce the unique hydroclimatological environment of the Pacific Northwest. Then I will go through the forest hydrology history of extremes. I'll then be spending time talking about the old versus the new framework for investigating extremes. Then I'll share with you case studies, some of which are done in my own research lab, but others have been done by research labs elsewhere, and I want to share those with you. Case studies on the effect of climate change and logging on floods. Then I will reflect on the state of science on logging practices' effects on droughts. Then I'll provide my concluding remarks. On the coast of the Pacific Northwest, there is an intricate relation between elevation and the form of precipitation, i.e., whether the precipitation falls in the form of snow or rain. This is because the temperature hovers around the zero freezing level, plus or minus a few degrees across this elevation range between sea level and all the way up to about 1,100-meter elevation up on the mountain. When the precipitation falls in the form of snow, it's usually wet snow, ready to melt. Either by the next rain event, which will melt the wet snow sitting on the ground, or intercepted by the canopy, or in the form of melted drip. This sort of environment is called snow transient and sometimes rain on snow environment for short. Melted drip is a unique mechanism associated with snow transient environment. In the snow transient environment, the energy under the canopy of the old forest in the form of long wave radiation is often higher than the energy above the canopy. When the precipitation falls in the form of wet snow and is intercepted by the old forest, such snow melt drips under the canopy, recharges the groundwater, and as long as the wet snow is falling. Tree removal, of course, suppresses this mechanism of melted drip, all at the expense of groundwater recharge. What characterizes this sort of environment is the fact that the rain on snow mechanism can occur anywhere between mean sea level and again about 1,100 meters above sea level. But there is an elevation around 750 meters where the conditions are optimal for rain on snow mechanism. Therefore, between sea level and about 1,100 meters, there is really a sweet spot for rain on snow phenomena. A quarter of a century ago, Tom Dunn, a distinguished world-renowned hydrogen morphologist and an outsider to the forest hydrology community, looking inward, stated, forest hydrology has a sad history of being embroiled in controversies that never seems to get resolved. He goes on to say, forest hydrologists could be recruited to defend any side of a debate because of our confusions about the various processes and their interactions in forest and streams has left much room for opinions and its attendant influences. Tom Dunn's statement is particularly true on the topic of forest and forest harvesting on peak flows and small watersheds and floods and larger watersheds. For over a century, every time a journal publication comes out claiming that forest cover affects large floods, more often by scientists from outside the forest hydrology community, the guardians within the core forest hydrology science community come back to disagree and instead defend an old perception of how the forest is supposed to affect floods. Such antiquated perception is best summarized by the following quote published by Calder et al. 2007 in Nature. Forest hydrologists generally agree that although forests mitigate floods at the local scale and for small to medium-sized flood events, there is no evidence of significant benefit at larger scale and for larger events. I shared with you on the lower part of this slide this review of the University of Lancaster's Ian Calder's book, Blue Revolution by Fred Pierce, which stated, Blue Revolution upturns some environmental apple cards, not for the hell of it, but so we can actually manage our environment better. I wondered, and I always will, whether what caused this pushback and some science-based convictions, or there is actually more to it. I came to the conclusion that the causes of the relentless pushback of any disruptive science and forest hydrology, like everything else in life, are multiple. These controversies have led to an ever-increasing schism between science, public perception, and certainly management policies. The public had always and continues to believe unquestioningly that the forests reduce flood risk. But calls for questioning the science, however, have been rare, perhaps in part due to the political sensitivity of the topic, and that's not my own words. These are those of Diwali 2003 and Stednick 2008. Diwali in 2003 stated, is there more to the forestry and floods issue than a red herring raised by anti-development factions? Brinj Zeal in 2005 asked the question, is there more truth to the public perception than has been acknowledged by the scientific community? Again, as a reminder, the old perception claimed that the forest or forest harvesting had no effects on larger floods. And large is often defined as events with a return period larger than 10 years, and that the effects on floods decreases with an increase in the flood event size. Labeled as a dogma by some, such perception has been reinforced by a century of peer-reviewed literature. Where the effect of harvesting on the magnitude of a flood event has been defined by the difference in magnitude of pre- and post-harvest floods when both are generated by the same storm in the rain environment or the same melt season in the snow environment. Such a framework pairs the pre and post-harvest flood event chronologically, and we refer to that as chronological pairing framework, CP for short. In 2009, we published a paper where we called upon the forest hydrology community to abandon the old and adopt instead the following definition for the effect of harvesting. Where the metric that define the effect of harvesting on the magnitude of the flood event is the difference in magnitude of a pre and post harvest floods when both are of the same frequency and not the same chronology. Therefore, instead of guiding the research investigation by what is the difference in magnitude between a pre and post harvest floods, when the watershed is driven by the same storm input, it must be guided by what is the difference in the magnitude of an event when the pre and post-harvest floods are of the same frequency. Leopold and Langbain in 1963 stated the vitality of a branch of science is a reflection of the magnitude or importance of the question on which its students are applying their efforts. The new framework that we have been using and been calling for the last 20 years is called frequency pairing framework as opposed to chronological pairing framework. The research question or hypothesis is the most important step in any science investigation, as it affects the experimental design meant to isolate the effect of a disturbance, forest harvesting in our case, on the system response, whether it's a floods or droughts or landslides. The old experimental design of chronological pairing have guided just about everything published in peer-reviewed work for over a century and counting. I quote from Kieng 1995 that misconception in archival science are often not easily or quickly corrected and need wide recognition if they are to be overcome. In 2009, we called for a reevaluation of the past studies and the century-old paradigm that shaped the science perception of forest floods and the biophysical environment. This slide shows a list of the publications since 2009 and even since 2004. We have published a dozen peer-reviewed journal papers analyzing old and new pre- and post-harvest flood data. And all studies led to diametrically opposite conclusion to the prevalent CP-based perception. We basically, this new framework turned the table 180 degrees on the effect of forest harvesting on the old perception. And the newly emerging perception as a result of the FP-based studies can be summarized in 3 points. Harvesting affects events of all sizes. The effects of harvesting increases with event size. And in most cases, there is no apparent threshold of flood size beyond which harvesting has no effects. Studies highlighted in blue on your left of the slide applied both the CP and FP framework to the same data sets to illustrate how the two frameworks do not lead to the same outcomes, especially on the effect on larger floods. So Why the experimental design that guide forest hydrology should pair by equal frequency and not equal chronology, like equal storm input or equal snowmelt season? Simply put, because the causes of floods, and at times these causes are referred to as drivers of the floods, are actually multiple. For instance, floods in the snow transient environment are driven by the amount of snow on the ground, the energy melting the snow, the state of watershed wetness prior to the event, the potential rain falling on the melting snow. These climate factors are not only multiple, but also chancy. Chancy really means that they are randomly occurring over time. It is very critical to note that these hydroclimate drivers are necessary, but not sufficient to cause a flood of a certain severity. And let me repeat that. It's critical to note that these hydroclimate drivers or factors are necessary, but not sufficient to cause floods of a certain severity. Here comes the role of landscape features in either amplifying or reducing flood potential. The elevation distribution within a watershed, whether the watershed is mountainous or gentle or even a plateau-like topography. Gentle or subdued terrains are more prone to much higher flood risk than mountainous terrains. Why? In subdued terrains, the entire watershed is contributing melt and runoff is synchronized. Runoff reaches the outlet in synchronized ways. Unlike in mountainous terrains where snow melt from different elevation bands in desynchronized fashions. The aspect distribution within a watershed plays a huge role in either synchronizing or desynchronizing melt and runoff. Like south and west exposed slopes deliver runoff to the outlet at different times than north and east exposed slopes. Above and below ground storage facilities and watersheds, such as soil, lakes, marshes, wetlands, floodplains, also play a huge role in slowing down the runoff and hence mitigate floods. The stream network in a watershed also plays a huge role in either synchronizing or desynchronizing runoff delivery to the outlet. And then the chief of them all is the forest cover. It's critical that we pause for a moment to point out that the CP-based story that you hear all the time in the media about the role of forest in mitigating floods is the following. Remove the trees, you suppress evapotranspiration, hence you leave behind wetter soil. Therefore, more runoff. And remove the trees by logging, there is more energy to melt the snow in a clear cut. That's the story you hear all the time, until maybe 2 years ago, since the November 2021 flood event. Such a tree or stand level story told by experts about the role of forest on floods is incomplete and outright misleading. Because, as I will demonstrate later through the case studies, the role of forest in mitigating the floods lies not at what happened at the tree or stand, what happened to the hydrology at the tree or stand, but at the watershed scale. And the larger the watershed, the larger is the causal power of the forest in mitigating floods and droughts. This is why and how the frequency pairing frameworks turns the table 180 degrees on the old perception of how forest affects the floods, especially more so on the larger floods. It's quite interesting that, as you will see later on, what empowers the forest in mitigating the floods and the droughts is actually the physical features of the landscape, again, in the form of mountains, topography of the bedrock, topography of the surface, aspect distribution, so storage below the soil storage below the surface, lakes, wetlands, etc. It's interesting because we often think of the landscape characteristics that I just listed as static features, not changing over time. Not changing over time, when in fact, as a result of climate, their role in affecting floods becomes random over time as well. And I can provide examples. The stream network actually expands and shrinks as a result of the state of wetness. And more expanded stream network make the watershed much more efficient in delivering runoff to the channel network. And therefore, the stream network, which you see as blue lines on a contour map, is not a static feature of the watershed. It's actually a random. Lakes and the amount of storage still available in lakes at the time of an event changes from one storm to another. And this is why lakes actually become, the role of lakes become random over time. Soil storage is affected by state of wetness of the watershed. And therefore, depending on the state of wetness of the watershed, the soil storage become itself, the role of it is a random variable. So therefore, it's not just the climate factors that affects floods are randomly occurring over time, but also the so-called static physical features of the landscape of the watershed are also, they have a role that is randomly changing over time as a result of the climate. Then comes the role of disturbances of all kinds, which can further amplify the potential of floods and droughts. The forest cover changes by logging, beetle infestation, and wildfire. Urbanization, agricultural practice, mining, global warming, and climate change, all of these are disturbances that could actually, that will amplify the magnitude, the frequency, and the duration of these extremes, floods, droughts, and landslides. In summary, drivers of floods are multiple, but also chancy. Chancy, that means they actually change randomly over time. The hydroclimate drivers are necessary, but not sufficient to cause a flood. Landscape features play the biggest role in mitigating or amplifying floods. Landscape features play the biggest role. That's a repeat. Bon. Since the drivers of floods are multiple and randomly occurring over time, the severity of a flood event increases when some of the drivers coincide in time. If you recall the November 2021 flood event, we have wet soil condition because it has been raining for the last many weeks before the November 2021 flood event. Then we've got a lot of snow, mid to high elevation on the slopes. But we also had atmospheric rivers and a couple of them back to back. So when some of these factors are actually coincide, then of course the flood event is going to be much more severe. Since the same flood event of a specific magnitude or severity can be produced by many combination scenarios of these drivers, every flood event of a certain magnitude occurs with the frequency, meaning every flood level or severity is a class of event, not a single event. Therefore, the only way to make the science of floods defensible is to investigate it within the magnitude frequency relation we hydrologists call the flood frequency distribution or flood frequency curve for short. The flood frequency curve or distribution is characterized by the long-term average or mean of all floods the variability around such an average, and a third parameter called the skew, which is a measure of the extent to which the curve deviates from the bell-shaped or normal curve. As you can see from the lower panels on the slide, an increase in the average flood or mean shifts the curve up. An increase in the variability steepens the curve, while the skew affects the curvature to be concave and mild or convex and steep. If the flood frequency distribution is used for predicting floods, so is the understanding of how the environmental controls are affecting floods. That understanding must be in a probabilistic framework, meaning in the flood frequency distribution framework. We postulated in several of our already published studies that forest disturbance-induced suppression of evapotranspiration, increases in the amount of energy available for snowmelt, forest disturbance-induced synchronization of runoff, and forest disturbance-induced soil disturbance, all of these contribute to increasing the amount of moisture available for runoff, and combined, they all increase the mean of the flood frequency distribution and therefore shift the flood frequency distribution up. We also postulated in some of our papers that forest disturbance-induced wetter soil, because of the suppression of ET, forest disturbance-induced disturbed soils, forest disturbance-induced synchronization of runoff, forest disturbance increases in the amount of energy available for snowmelt, and forest roads, which intercept subsurface runoff by the cut banks and increase stream density through the ditches that are actually draining these forest roads. All of these can increase the efficiency of delivery of runoff to the watershed's outlet, which in turn increase not only the variability, but potentially the skew of the frequency distribution. There are cases that forest disturbance induces desynchronization of runoff, which is expected to occur more so in the snow and snow transient environments and not as much in the rain environment. Desynchronization of melt can decrease the efficiency of delivery of runoff, to the watershed outlet, which in turn decreases the variance and potentially the skew. This is the only case where the two pre and post-harvest flood frequency curve converge at the end, and therefore, the larger the event, the smaller is the effect of forest harvesting or forest disturbance. But in most cases, the two flood frequency curve, pre and post disturbance, are actually diverging based on the work that we've been doing over the last 15 to 20 years. Therefore, the only way to isolate the effect of any disturbance on floods, whether it's climate change or wildfire or logging practice, is to compare two flood frequency distributions with and without the disturbance, i.e., two flood frequency distributions equal in everything but for the disturbance. This is the only causal and hence defensible framework to study the relationship between forest and floods, or floods and any other disturbance. Disturbance, as you see on the slide, can increase the mean, the variability, and the skew of the frequency distribution, hence increasing the likelihood or frequency of extremes, which is the shaded area under the upper tails. Extremes, one of the first idiosyncrasies of the science of extremes is that extremes can be highly sensitive to even small changes in mean, variability, and skew of the frequency distribution. And this is one of the three main idiosyncrasies of the science of extremes that I'm sharing with you today. Therefore, this is one of the reasons why nobody should be surprised with how frequent floods are becoming as a result of a multitude of causes: wildfires, clear-cut logging, global warming, and of course, you've got the urbanization and everything else associated with land use changes. While frequency pairing, or the frequency distribution framework, has evaded forest hydrology for over a century, it is absolutely not a new science. It is, as a matter of fact, common practice in many other areas of hydrology and climatology, and is a recognized methodology by the International Panel on Climate Change for evaluating the effect of a changing climate on the magnitude and frequency of weather extremes. I just want to share with you a thought. It's because I come from outside forest science. I have a civil engineering undergraduate and graduate training. When I first joined the Faculty of Forestry, I started analyzing pre- and post-harvest flood data using frequency pairing without even blinking my eyes. Frequency pairing came to me as natural. That's the way I thought it should be done. But when I started analyzing data with this framework, I found that the outcomes of that framework are diametrically opposite to the well-established perception in the literature of forest hydrology. Over the last 20 years, such a framework has been further developed to evaluate the extent to which, and this is the most important part of it, such a framework has been further developed to evaluate the extent to which specific extreme events such as heat wave, wildfire, atmospheric river, or flood is caused by, say, global warming or land use change. This now has been referred to as attribution science. Attribution science has been developing rather aggressively over the last 15 to 20 years, particularly by climate change scientists. Attribution science is driven by the needs of policymakers, insurance companies, and lawyers. Since 2015, we have pioneered the use of attribution science in several winning court cases related to the effect of logging practices on floods in BC. Now about the second idiosyncrasies of the science of extremes. The wider literature tells us that the flood frequency curve or flood frequency distributions could manifest as either steeper, between parentheses, heavier, or milder, between parentheses, lighter upper tails. There is support in the literature for the hypothesis that under pristine conditions, prior to any disturbance, including climate change, the flood frequency distribution in the Pacific Northwest are generally lighter, have lighter upper tail, i.e. milder in slope, as you see on the panel on the right-hand side of the slide. And the mildness of the flood frequency curve makes floods in the Pacific Northwest generally super sensitive to disturbances of any kind, be it climate change, urbanization, agricultural practices, and or forest disturbances by logging and or wildfire. Note, by comparing the left and right hand panels on the slide in front of you, how the same increase in magnitude of floods caused by a disturbance, the same push up, because when you push the curve up, the magnitude has increased. When you compare the left and right hand panels on the slide, notice how the same increase in magnitude of floods caused by a disturbance will translate into much larger changes in the return period or frequency of floods in the case of a lighter tailed flood frequency distribution on the right panel. Then, voila. You see the milder curve on the right panel, right? The 100, because the curve is mild, the 100-year become a 10-year event, which means the flood level that we used to observe once every 100 years or experienced once in every 100 years. Now we are experiencing it every year, every 10 years. So the 100-year flood level have become 10 times as frequent. On the other hand, when the curve is steep, the 100-year may become twice as frequent. The moral of the story is that in the Pacific Northwest, as well as in the interior of British Columbia and in the coastal Pacific Northwest, as well as in the interior continental snow environment, the flood frequency curve has a lighter upper tail, which means is milder in slope. That's under pristine condition, before disturbance. The curvature, which means really that the curvature of the flood frequency curve can affect the change in return period with a greater effect for larger return periods. This brings about the third idiosyncrasy of the science of extremes, namely, the larger the watershed, the more sensitive the hydrology and hence the geomorphology is to disturbances. In other words, the same level of disturbance will result in bigger effects on floods and larger watersheds than in their smaller headwater tributaries. This is because as the watershed gets larger, there is more opportunity for the physiographic characteristics or the physical characteristics of the landscape or the watershed to actually mitigate floods. Larger watersheds have larger elevation ranges, much wider range of aspects, more opportunity for below and above surface storages, more opportunity for desynchronization of flows from various tributaries. All of these will make the flood frequency curve milder as the size of the catchment increases, which tells you that in this FP framework, larger watersheds are much more sensitive to disturbances in general, logging practices in particular, than the smaller tributaries. By the way, these flood frequency curves that you see on the slide have been developed using actual observed regional flood data from British Columbia. Using this frequency distribution framework, I'm going to share with you 5 case studies to illustrate how the hypersensitivity of floods to climate change and logging practices in the rain and the snow transient environment of the Pacific Northwest. Some of the case studies are out of my research lab, but others are done by colleagues in other research labs outside UBC. For instance, our colleagues at the PCIC, the so-called Pacific Climate Impact Consortium at the University of Victoria here in BC, published a paper applying attribution science to investigate the extent to which global warming contributed to the 2021 flood event in the southwest of BC. As you recall, the 2021 flood event caused wide flood damage, historically the largest in the record, and cost damage in the estimates of billions of dollars. It actually triggered a couple of class action lawsuits, particularly against the BC government. I want to share with you my thoughts on some of their findings related to how global warming affected the entire flood frequency distribution in the snow transient zone of coastal BC. This figure in front of you, adopted from their publication, is showing how the flood level in the Coldwater River, which used to be experienced once every 100 years, is now experienced once every 23 years as opposed to as a result of global warming. This means that the 100-year flood event magnitude is becoming 5 times more frequent. The patterns emerging from this figure are the most revealing to me. Number one, the pre-climate change disturbance, which is the lower curve, is actually light-tailed or mild in slope, corroborating our hypothesis that in the Pacific Northwest, in the snow transient zone, the pre-disturbance flood frequency distribution should be light-tailed and not heavy-tailed, as shown in the graph. You see that black curve, in the panel? Point number two, emerging pattern from this study, climate change affects floods of all sizes. Point number three, the larger the flood, the larger the effect on the magnitude, and most importantly, the frequency. There is a tendency, as you could see there, the larger the event, the more frequent it becomes as a result of global warming. They have shown this, the co-authors from our colleagues, the co-authors from PICIC, have shown this to be the case in 7 coastal watersheds, varying in size from about 200 to over 1,200 square kilometer. Policymakers, regulators, and professionals should be concerned about not only climate change increasing the magnitude and frequency of the large and very large floods like the 100 and the 200-year flood event becoming more frequent, but the fact that small and medium events, less than 20 years, less than 50 years, are also becoming more frequent. It is the small and medium events which are more responsible for the destabilization of the channels and an increase in sediment production, transport, and downstream deposition. In my opinion, and this is a very critical facet, the frequency dimension which has evaded forest hydrology for over a century and counting is the more important of the 2 flood attributes, namely the magnitude and the frequency, because such increase in frequency and hence duration of high flows will be very taxing on water quality in community watersheds, very taxing on fish in the streams, very taxing on downstream infrastructure, and very taxing on the human lives. Moving on to other case studies on the effect of logging practices in the Pacific Northwest on floods. I share with you today one of our studies that evaluated the effects of logging in the headwaters of the snow transient environment in the state of Oregon. My ex-graduate students by the name of Nick Rong, who is now working for the private sector, investigated the effect of logging practices using long-term post-harvest peak flow data at 9 pairs of control treatment watersheds. This is using real observed data in the field. These watersheds, these headwater catchments vary in size between 0.5 to 1.1 square kilometer. They vary in physiography, and they vary in post-treatment peak flow data from 20 to 50 years. They also vary in treatment. The treatment varies from clear cut to patch cut to selective logging with and without forest roads. Case study number 2 is Coweta Creek. The results reveal that the effect of logging on peak flows are sensitive to cut rate at Coweta, with larger effects on magnitude and especially frequency for larger event. As you could see from the panel on the left side of the slide, the larger the peak flow event, the larger is the effect on both magnitude and especially the frequency for cut rates particularly the ones exceeding 30%. The small difference between the two red flood frequency curves, which based on the legend represent peak flow data that are observed with no adjustments for hydrologic recovery caused by the regen and the recovery adjusted curves. These are two curves. And the small vertical difference between the two red flood frequency curves with and without recovery adjustment is indicative of little recovery caused by forest regen in the first 20 years after logging. This is what I kept on repeating over and over again, that even data from south of the border, carefully collected by the US Forest Service in these paired watershed studies, if you actually analyze them using the right framework, it shows that the first 20 years, the regen has no bearing, not much of a bearing on the recovery of the impact created by logging. And I think no one should be surprised, frankly. Why? Because of the story that I've spent half an hour talking to you about the power of the forest in mitigating floods or droughts or landslides. Does not lie on the stand or on the tree, does not lie on the hydrologic functionality of a tree or a stand. It lies in the physical characteristics of the landscape. It is the physical characteristics of the landscape that empower the forest to actually mitigate floods. Case study number 3 is on Fox Creek. Fox Creek experimental watershed is very unique indeed. I think we're very lucky to have Fox Creek. The results at Fox Creek reveal that the effect of logging on peak flows are way more sensitive to even 25% patch cut rate, with the larger effects on magnitude and especially frequency for larger events. As you could see in there, the difference between the black curve, which is pre-harvest flood frequency curve, and the red curve, which is post-harvest flood frequency curve, is showing that the 30-year is becoming a 3-year event, and the 10-year event now is experienced every year. And nobody should be surprised. Why? Because the peak flow frequency curve is very mild, and it's concave down. And what makes it very mild? What makes this curve very mild at Fox Creek? Well, it's the foggy drip. It's the foggy drip, yes. A cross comparison of the slope of the frequency curve between the 3 control watersheds at Coweta, A.G. Andrews, and Fox revealed that Fox Creek had much milder slope peak flow frequency curve. We attributed the mildness of the frequency curve to the foggy drip, which contributed 30% of the annual water balance at Fox Creek. That means if you have a bucket and you're measuring the amount of runoff over the year at the outlet of Fox Creek, 30% of it is contributed by foggy drip. Foggy drip, that is when the cloud hits the canopy, right? That cloud condensate and end up falling as a drip to actually recharge slowly but surely the groundwater. This is different from melted drip. And fog interception is sometimes called the occult precipitation. So foggy drip, right, increases the base flow, which translates into lower variability of peak flows around their mean, and hence milder flood frequency curve. The milder flood frequency curve means more hypersensitive floods to logging. You find this extremely fascinating because This is definitely diametrically opposite to the chronological pairing framework. Case study 4, the A.G. Andrews. We're still in Oregon. The results reveal that the effect of logging on peak flows are way less sensitive to even 100% clear-cut rate at A.G. Andrews. A.G. Andrew 1, which is treatment. A.G. Andrew 1 and A.G. Andrew 3, the top two panels, have the highest elevation range, therefore the most opportunities for desynchronization in this rain on snow environment. You could see how this is a very good case where you log the trees and because of a high elevation range between the outlet and the ridges, and because of the intricacies of this rain on snow environment, where lower elevation, more of the perceived fall in the form of rain, higher elevation, more of the perceived fall in the form of snow. In this way, you've got a lot of desynchronization, even before logging. But when you actually log, even in clear-cut logging, you further the desynchronization, and you may end up with a little effects on the peak flow at these headwater catchments. It tells you that it tells you that the physiographic characteristics of the watershed, the physical characteristics of the landscape, are the ones that actually empower the forest are the ones that dictate the effect of logging. It's not what happened at the tree or at the stand. It is what happened to the flood frequency curve as Mother Nature integrate the effect of all the trees and all the stands within the landscape across the watershed and over time. And that space-time integration in the form of magnitude-frequency relation, which is the only framework that makes the scientific investigation causal and therefore defensible, is telling you that it is the physiographic characteristics of the watershed and the climate characteristics that are empowering or not empowering the forest and actually mitigating the hydrology and the geomorphology. In the modern science, this is called causal emergence or downward causation. Namely, it's not what happened at the stand or the tree that actually dictate the role of forest in affecting floods or droughts, right? It's a top-down causation. The causal power is a changing of the forest and affecting hydrology is actually changing as a result of the landscape features. You've got macro scale hydrology like energy and water balance at the tree and at the stand. That's necessary, but not sufficient to tell a story about how the forest cover is actually likely to affect the hydrology and the geomorphology, right? Unless you step back and look at the forest at the larger scale, there is no way of revealing the causal power of forest and affecting the hydrology and the geomorphology. And I mean it when I say hydrology and geomorphology. Why? Because if you affect the flood regime by disturbance, you affect the entire ecosystem in the watershed. You affect the sediments, right? You affect fish in the streams. You affect water quality, right? And therefore, if the landscape features are empowering the forest and mitigating the hydrology and floods, isn't that about time to actually move from the stand level management that have guided forestry in the Pacific Northwest into landscape management? They don't call it landscape for nothing, because that's where the causal power of the forest lies. It's in the physical characteristics of the landscape and the physical characteristics of the climate. And Fox Creek, in terms of physical characteristics of the climate in the form of fog drip or melt drip. Although both Andrews 6 and Andrews 10 have a smaller elevation range, these are the lower two panels on the left-hand side. Although Andrews 6 and Andrews 10, which are two treatments in the Andrews, have a smaller elevation range, their elevations are further away from the 750 meter above sea level. That elevation recognized to be the optimal elevation for rain or snow to occur in the Pacific Northwest. Andrews 6 is higher elevation between 878 to 1029 meter above sea level, therefore more snow dominated. And Andrews 10 is lower elevation, sitting between 460 meter to 679 meter above sea level, which is more rain dominated. Between 6 and 10, Andrews 6 showing more effects on peak flows is sensible, because the snow melt generated peak flows are more susceptible to synchronized runoff generation than rain generated peak flows. Moving on, I'd like to, before closing, provide you with some reflections on the effect of logging practices, at least in the way we have been doing over the last several decades, on droughts. There are three mechanisms induced by clear-cut logging practices, which will exacerbate the severity, the frequency, and duration of droughts. The first mechanism is via forest roads. Forest roads will act as streams through the creation of ditches and rerouting of water. Forest roads increase stream density and subsurface runoff interception through cut banks, all at the expense of groundwater recharge. And this is how forest roads end up exacerbating droughts through logging practice. Number two mechanism, in the snow transient environment, the energy under the canopy of the old forest before logging in the form of long wave radiation is often higher than the energy above the canopy. When the precipitation falls in the form of wet snow again, and it is intercepted by the old forests, such as snow melts and fall in the form of drips, liquid water, under the canopy and recharges the groundwater. And as long as the snow is falling, tree removal suppresses this mechanism of melt drip. Again, all at the expense of groundwater recharge that is meant to feed the channels during the driest period of the year, late summer and fall. The third mechanism associated with forest practices, particularly clear-cut logging and subsequent regen or replanting, is the fact that younger regenerating forests in the cut blocks have higher rates of transpiration. Recent studies out of Oregon State University, colleagues of ours, have shown that within 10 to 15 years after clear-cut logging, the region started consuming 50% more groundwater than the older forests that were logged. All, of course, at the expense of groundwater that is meant to feed the channels during the driest periods of the year, again, late summer and early fall. This is how clear-cut logging, particularly on the coastal environment, is exacerbating the magnitude, the frequency, and the duration of droughts, all in the background of global warming, heat dome and heat waves, and wildfires. What I wanted to share with you is a very interesting situation, is a circumstantial evidence of the power of melt-drip. This last summer and fall, and early fall, as well as last summer and the entire fall of last year, we have been experiencing, like everyone else, the most severe droughts in the last maybe 100 and some years. The Sunshine Coast is also typical. Our Sunshine Coast in BC is also typical of this snow transient environment. The Sunshine Coast Regional District, this slide shows the timeline to lifting the state of emergency by the Sunshine Coast Regional Districts. It reveals the power of, or the role of melt-drip. In 2022, stage 1 started from May 1st to July 27, 2022. Then by August, they escalated it to stage 2. Late August, it became stage 3. That means the streams are becoming drier. August 31st to December 13, supposedly, we are already in the precipitation season. August 31 to December 13, it was a stage 4. And then it was lifted in February 6, no restriction. Unlike this year, last year, by the time it's mid-October, the temperature went very low, mid to high elevation. And therefore, the precipitation was falling mid-October all the way to end of December and January, mid to high elevation. But because the temperature were low, mid to high elevation, all the precipitation was falling in the form of wet snow. And that wet snow ended up filling the Chapman Lake, which is the community watershed, right? And therefore, we remain in stage 4 all the way to December. It took basically 4 to 5 months from September, October, all the way to end of January for that precipitation to slowly fall in the form of wet snow, melt in the form of drip falling on the ground, infiltrating slowly and surely to recharge the groundwater. But of course, the lake, that groundwater takes months for it to travel below the surface and end up filling up the lake. And that's when the Sunshine Regional District end up lifting right, the state of emergency only in February. But the data shows that the precipitation that has fallen from mid-October all the way to January, mid to high elevation, is actually in the form of solid precipitation and not rain. And that, in my opinion, the best illustration of the power of melt drip and actually recharging the groundwater, right? So this was not the case for this fall because the temperature didn't plummet down quickly as it happened in October 2022. I thought this is a circumstantial evidence of the power of melt drip in the snow transient zone. To conclude, we must use science of extremes or attribution science for designing policy and guiding professional practice in the management of forest and water. We need to abandon, stand level in favor of landscape management and the practice of forestry, because the power of the forest in mitigating the risk to hydrology and geomorphology lies not at the tree or stand level, but on the watershed scale. And the larger the watershed, the more powerful the forest in actually mitigating the hydrology and geomorphology. Relying solely on an increase in size of downstream infrastructure, such as culverts, bridges, and dikes, will not meet the objective of any flood management strategy because it does not account for the fact that events smaller than the design capacity are becoming much more frequent, which means these infrastructures are going to fail geomorphically. They're going to be battered with a lot of geomorphic and work and therefore destabilize these structures. Future downstream flood and drought management strategies must be in sync with our land use and forest cover related policies in the upland. Thank you very much.
Thank you, Eunice, for your talk, as always. I have a few questions here from the participants, and I can summarize them in general. One thing that came up in many of the questions is, what does the type of forest, the combination of different types of trees and other biological plant elements that are in a full stand forest do to mitigate flood, or do they have any effect at all?
Can you re-articulate the question again, please?
The type of forest, meaning the diversity of the species in a forest, does that affect the flood regime?
It certainly does. The deciduous trees, for instance, have a very different hydrologic functionality than the coniferous trees. And therefore, deciduous trees could actually play a big role in particularly in desynchronizing the melt, or synchronizing it. In the Smithers lawsuit, Jacqueline, in the Smithers lawsuit against the log and against actually BCTS, the watershed was 4 square kilometers in size. 2/3 of it is actually covered with coniferous and 1/3 with deciduous. They took 50% of the coniferous, which is 1/3 of the watershed forest. So the cut rate, the actual cut rate is 30%. And it happens to be, of course, coniferous. Before logging, the snow from the deciduous part of the watershed, because the deciduous are sitting in one corner. The snow from under the deciduous melt first. Then the snow from under the coniferous before logging melt second. So the melt was desynchronized before logging. When you log 30% of the watershed, which is coniferous, suddenly the 30% cut block is melting simultaneously with the 30% of deciduous. Therefore, you've got now logging end up synchronizing the melt. Therefore, while the actual cut rate is 30%, I told the judge and the lawyers that the effective cut rate is actually double that, 60%. Why? Because in many situations, it's not about what you cut or how much you cut. It's also what you leave behind after cutting. Because what you leave behind may end up synchronizing the melt or desynchronizing it, depending on the situation. So the effect of logging depends not just on the cut rate, but on the location of the cut block, what else you leave behind. Therefore, the physiographic characteristics of the watershed, including the species composition.
So one additional to that, Eunice, and I don't recall this from your own work, but this has to do on what's the forest floor. Many of the observers here are asking questions about what happens when they spray these clear cuts. Does it impact it as well?
Well, they spray for a reason. They spray because they wanted to kill the deciduous so that it does not compete for moisture, and then also because they wanted the coniferous to grow more vigorously for the wood value in the future. So that's an unfortunate effect, because the deciduous plays a big role in the watershed. And of course, all of the spraying is chemical and it affects the water quality, and it has also other side effects.
Okay, so as we only have 5 minutes left, if I may ask you, and this comes up a lot in the questions too, how do we operationalize this new science of attribution and bring it forward to managing the forest landscapes on which our consumptive watersheds depend, to educate and both agitate government and forestry industries? How is the community supposed to use this to understand how sensitive their systems are?
Well, I think it starts with with those who are making the policies, and therefore the policy makers, if they develop an appreciation of the science, they will then make sure that the forest management policies are actually using the peer-reviewed science. And if the policy does not change, I'm not sure the extent to which professionals who are stamping on forest development plans, as they have been for the last many decades, are going to change. Therefore, I do strongly believe that the buck stops at whoever is actually designing the policies. And I think economic analysis is necessary to find out at what cost we're going to continue doing forestry in the form of clear cutting, right? Because the cost is astronomical when it comes to damage. it is unfortunate that European countries have adopted a policy of replanting of trees for the purpose of using the forest cover to mitigate against an increase in flood risk caused by climate change, when in fact we continue to actually log like there is no tomorrow, when in fact our forest cover is our best natural protection against flood risk, particularly the increase in climate change, the increase in flood risk caused by climate change. As you could see from the data and the case studies that have analyzed, right, it appears that in many situations, the forest cover effect in mitigating floods is actually bigger than the effect of global warming on increasing flood risk, right? So that is the situation, Jacqueline.
So it is now 7:28. Julie and the others have some announcements they need to make at the end of this. Are you there, Julie?
I think it's Nancy who is gonna close us out. Is that still right?
Okay. Yes. Okay, Nancy. 7:29. Thank you, Eunice.
Thank you, Jacqueline. Thank you, everyone, for coming tonight. Nancy is speaking now, but I think she is muted.
You hear me now?
Yes, I can. Go ahead, please.
Okay. I want to start out thanking Eunice, and worldwide, our drinking water sources are threatened. And for example, in many communities, such as Peachland, Canada, our sister city, and Rockaway Beach, Oregon, our watersheds have been under extreme deforestation, affecting water quality and quantity in the last 20 years. However, in both Vancouver and Victoria, BC, their drinking watersheds are totally protected. Similarly, in Portland, Oregon, our own Bull Run drinking watershed is fully protected. No more logging or spraying. However, in the 70s and 80s, Bull Run was being logged. My mother, along with other community members, worked to stop this logging. The logging stopped in 1993. Today, Bull Run is a model of community watershed protection. Now it is our turn to be responsible and stand up and protect our drinking water sources. Please join us. No more logging and spraying within our drinking water source, no matter the ownership. Thank you.
Nancy, are you guys going to make an announcement for the next webinar?
Oh, sorry. Our next webinar, we are honored to have, which ties into this webinar, is Herb Hammond, a 40-year forest watershed expert who has written the books on forest ecology, and he'll be talking December 7th at 6 p.m. via Zoom.
Okay, thanks everyone. This is, I think, the end here. You'll get email follow-up with a link to the recording once it's posted on the Oregon Shores YouTube channel. And we appreciate your participation today. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Thank you, everybody.